So by now you should have watched the unsupervised part, right, and the generative models. We just had a very brief discussion about GANs, about generative adversarial networks in the video lecture. So I would like to show you some very recent and very nice trick related to training GANs, and you will see also more on this, on domain adaptation, on transfer learning, also in the exercise. You will also see it in the home assignment, and then for the next week I will ask you to watch the reinforcement, basically the chapter on reinforcement learning. Okay. So any comments, any questions before I show you this trick? I think it's a recent paper about 2 or 3 years ago, something like that. How is it going with the homework, by the way? Very time consuming. That's the adversarial effect, I would say. But hopefully it's helpful. Okay. Okay. So let me very briefly remind you what is the idea behind GAN. I will use a slightly different notation compared to what I used in the lecture. It will be sloppier, but hopefully you will still get the idea. Okay, so GAN stands for generative. Generative means that we would like to sample from the data distribution. We would like to build a black box that knows how to create new instances. So it's generative. Adversarial. I will exactly define what I mean by adversarial networks. I think probably it is nicer to call this adversarial training, because this is a way to train networks and not a specific architecture that you might understand from this title. But anyway, this is how it was called in the literature. So the idea is very simple. So suppose we have a black box, let me denote it by G, that generates data. Okay, so how we generate data, we have seen this in the video, right? We inject noise. Let's suppose this noise is Gaussian and zero mean and white with unit covariance, and the output is some generated instance. Okay, and we try really hard. We want to be as close, as faithful to the real distribution, to how our data samples look like as we can, right? And of course, the way we control this, we have a set of parameters here that we learn, right? Obviously. Now I'm going to, so when we talked about autoencoders, we had some loss function that distinguished us from the generated samples from the real samples, but then we can argue to death about what is the correct distance, what is the correct metric, what is the correct loss function to put. For example, will L2, the L2 norm, like PSNR, be an appropriate thing for images? You can argue that it's not, right? And there have been many attempts to do it by hand until this, in my opinion, brilliant idea came, which essentially tells you that let's learn this distance function together with the model. So we are going to put here a discriminator, let's denote it by D. This discriminator is fed with this fake data as well as with real instances. So let's denote real instances coming from some distribution. I will denote it by PD. Okay, D for this standing for data. Okay, and of course we have plenty of such instances, right? This is the actual thing that we are trying to generate. And let's say that essentially this x, of course, this is g of z, but we can also think of it as coming from this generated data distribution PG. It is fully parameterized by theta and the statistics of our noise. Okay, and this discriminator is going to give us binary labels, 0 or 1. So imagine that I'm trying to forge Picasso's painting, and there is a detective that tries to detect his forgery. Okay, so this is the game that we are going to play. I'm going to be as precise, as faithful to the data distribution as possible, and this detective, this discriminator, will try to catch my forgery. Okay, and of course it will be a neural network as well. It will have some other set of parameters. Let's call it phi, and we are going to train them together. Okay, so first of all, let's determine what is exactly meant by saying that this discriminator does a good job. Okay, so we are going to feed. I'm drawing this kind of a connection, but basically it means that I'm feeding it both with real data and with fake data. Usually, for practical purposes, it is done with separate mini batches with separate batch normalization that is done on the generated data on the real data. But again, these are technical details. So basically what I'm going to do, I'm going to take the logarithm of d. Okay, so let's take the logarithm of dx. Let's say I'm feeding my real data. Okay, so now I can interpret the logarithm of dx. D will produce something in the range between 0 and 1. Okay, and I can think of this logarithm as log probability density of my posterior distribution, of my class distribution. So I would like, on the real data, I would like the expectation of this to be big or small. So let's say 1 means real and 0 means fake. So on the real data, x is real data, right? So x coming from PD. On the real data, I want to maximize this quantity, right? Now, on fake data, let's take the fake data. Okay, so it is generated by injecting this random noise, right? It will be log, I'm leaving some space here, dgz. So this is the fake x, right? Let's call it x hat. It's the generated x, right? And I would like the discriminator to give low values here, right? So I would like to minimize this expectation, or what is typically done, I'm taking 1 minus d, which again I'm interpreting this as the class probability, as the fake class probability, and I want to maximize this expectation, right? And of course, this maximization is done over d. I write it over d, but obviously it's the set of parameters that parameterize d. It's the set of parameters phi that I wrote here. Okay, so I will write it in this slopey way. It's optimization over d, but d belonging to this class of parametric models. Okay, and let's call this. Of course, you see it depends on g. It depends on g, right? So let's call this maximum value. Let's call it j of g. Okay. So out of all possible, so you give me a generator g, and I will give it a score. So this score tells me how well I'm doing. Okay. So you see, we actually didn't select the loss function that we are building, where we didn't select by hand some L2 distance here or some distance to some another distribution. Actually, this maximization problem essentially created a distance function for us. It's not a distance in the sense that it is not a metric, but it's some score that we can assign a generator, right? And what we are going to do next, we are going to try to bring this thing to minimum over all possible generators. Of course, meaning that we are actually optimizing over theta, right? Okay. So again, our training is done in the following way. We are first building this score G, and the generator has an adversary. This adversary discriminator, this D, plays as well as it can. That's why we're doing this maximization. It tries, given the generator, it tries to maximize its performance. It maximizes its performance as a detective, right? And then given that this is how we are going to be judged, we are trying to find the best generator that can fool this discriminator in the best possible way. Okay. So this is called adversarial training, and networks constructed this way are called GANs. Okay. So far, so good. Okay. So again, let me rewrite this objective. So we are maximizing over D. This is JG, right? We are maximizing over D this expectation of X belonging to PD log dx. Let me write it in a slightly different way. Here, instead of dealing with the noise Z that is fed into the generator network and that produces the fake instance, let me directly write the distribution of these fake instances. This is our PG, okay? This PG, okay? You can just think of it as some intricate nonlinear transformation of the white Gaussian noise, right? Actually, you can exactly tell by simple theorems in probability theory how the distribution will look like when you transform it this way. Okay? And here I write again log 1 minus dx. So it's still x, but here x is distributed according to PD, and here x is distributed according to PG. Okay? Let me actually write it explicitly. Let me write it using probability density functions. Again, it's minimum over D. Integral of log dx pdx. So PD here is the density function, okay? Plus log, sorry, it's maximum, of course. Thanks. Log 1 minus dx pgx dx, okay? So I'm just writing the expectations as integration with respect to the corresponding density functions. Okay. Now pay attention. These terms, this term and this term, they are all non-positive, right? It's a log from a number that is smaller than or not greater than 1, right? So they are non-positive. And these quantities are non-negative, right? These are density functions. So if you want to maximize this, what do you mean by maximizing over D? It's D as a function from x to let's say 0 and 1. Okay, it's a function from Rn to 0, 1. And this integration, let's do it pointwise. Okay, let me write it pointwise. I will fix x. Let me fix x, and then I will maximize. Let me call dx, let me call it a. This is my variable. So the value that dx assigns to a point at point x. Okay, so it's maximization over this a. It will be, let's call PD at point A. Let's call it, let me use a different color. Let's call it P, and let's call this Q. Okay, once we fix x, these are just scalars, right? So it's maximization of over A of P times log A plus Q times log 1 minus A, right? So let's call all these function as f function of A, okay? So again, f function of A is P times log A plus Q times log 1 minus A. We can take its derivative with respect to A, of course, equated to 0, right? Well, I want to maximize this. So we have a closed form expression here, right? So it will be P over A minus Q over 1 minus A, right? We equate these to 0, and after some trivial algebra, we get A equals P over P plus Q, right? So let's again substitute what P and Q and A mean. A is dx. This is true for every x, obviously. P was PD at point x, and Q is PG at point x. Okay? So we have a closed form for our generator, right? Sorry, for our discriminator. Okay? So this is our closed form for the discriminator. Let's now substitute it back to the value of the objective, right? So this was JG was the maximum over that expectation, right? Over D, right? So basically we have this expectation over X coming from PD of log dx plus expectation of X coming from PG log 1 minus dx. And now we have a closed form for dx, right? So let's write it, the solution that realizes this maximum. We have E X coming from PD log PDX over PDX plus PGX plus the expectation of X coming from PG log and 1 minus, you see this denominator, it will be obviously PGX over PDX plus PGX, right? Any objections? Okay, so this expectation, so you see you have expectation over PD of log, a fraction, a ratio, the same PD in the numerator and some other thing in the denominator. How does it look like? Same thing here, of course. Does it look familiar? Looks like the Kullback-Leibler divergence, right? So just a reminder, Kullback-Leibler divergence, dKL between two distributions, let's call them mu and nu, was the expectation over mu of log, let me be sloppy, it should be what is called the Radon-Nikodym derivative of two measures, one with respect to the other. Let me just write it in the form of densities here, like this, okay? And if you want to be completely precise, it's d mu over d nu, okay? So this was the Kullback-Leibler divergence. So what we have here looks sort of like the Kullback-Leibler divergence, right? So let me define another density. Let me call it Q. Q will be half PD plus half PQ, and it's very easy. It's a convex combination, right? It's very easy to show that this is also a probability. It's also a PDF. It's a valid probability distribution. Okay. So then up to some trivial constants, what I have here is proportional to the expectation, let me write it like this, expectation with respect to PD of log PD over Q plus expectation, or let me write it 1/2 expectation X going X from PG log PG over Q plus some constant. Okay, and added this 1/2 because basically what we have here again is 1/2 Kullback-Leibler divergence between PD and Q plus 1/2 Kullback-Leibler divergence between PG and Q plus some constant. And of course, this 1/2 and this constant, they don't affect the minimizer when we minimize this with respect to the generator, right? And this distance has a name, so let's just say that what we are doing, we are minimizing with respect to G. Let me write it as a minimization with respect to PG. Okay, so this is we have some parameterized form of the distribution of the generated samples. We are minimizing this 1/2 Kullback-Leibler divergence between PD and Q, and Q is a midpoint between the two distributions, right? Plus 1/2 KL PG Q. And this is also a divergence, and it is called the Jensen-Shannon divergence. We can think of it as a Kullback-Leibler divergence that has been fixed in some useful way, but essentially does the same. It measures distances between two distributions. It cannot be smaller than 0. It is not symmetric. It's still not symmetric. You can actually symmetrize it. But for example, a nice property. So basically, what we have is minimum with respect to PG. Let's call it JSD, PD, PD, and PG. Okay, so this is the definition of the Jensen-Shannon divergence. It's the divergence between PD and PG. You measure basically two Kullback library divergences. We have PD here, PG here. This is their midpoint. I call it Q. So we measure this distance, we measure this distance, and their arithmetic mean gives us the JSD. Okay. For example, a very useful property that makes it almost a metric, that JSD equals 0 if and only if PD equals PG. Okay, so if we find the global minimizer of this thing, we know that the distribution that we created is exactly equal to the distribution of the data, which is, of course, what we are trying to do, right? Okay. Any questions? So essentially, this is what GAN training is doing. Okay. We are trying to minimize this Jensen-Shannon divergence, and it is going to be globally minimized when PD equals PG, or the other way around, where when our generator is so configured to make the data with the same distributions, and then of course they will be indistinguishable from the real data. Okay. And what is nice here that of course that we have this closed form expression for the discriminator. Now let me draw you a one-dimensional picture of what is going on here. And let's see that we might have some numerical issues. By the way, these numerical, what you see here is just a reinterpretation of GAN. These numerical issues that I'm going to show you, they will appear if you train it the standard way, right? This is just a mathematical interpretation of what happens inside GAN. So let me think of X as a one-dimensional variable. Okay, this is my X. And let's say this is my PD. Let's make it bimodal. This is my density. This is PD. This is the actual data density. And this is going to be my generated density. Okay? Okay? Of course, you can say that it's trivial to discriminate between the generated samples and the true samples. They have completely different distributions. So the way our form for the discriminator was PD over PD plus PG, right? So if you actually compute this, it will more or less look like this. Something like this. I'm not drawing the exact shape, but this is how it will look like. So you can see that the overlap between the distribution is practically inexistent, right? And the discrimination is a piece of cake. It's very easy to discriminate between the two distributions. But now you computed your discriminator, and from that discriminator you're going to derive the gradients by using backpropagation to drive the generator to improve its performance, right? Now let's imagine how the gradients of this expression are going to look like. So I care about d over dx. In this case, it's just a regular derivative because x is a one-dimensional variable of this dx. What is written here is dx, right? Let's take the absolute value of it. So you see the shape of this green function. So the derivative will be high here. It will be high here. It will be high here, and it will be high here. It will vanish elsewhere. I mean, it will not exactly vanish, but it will be practically zero in case of these Gauss. And if the distribution is really supported on some bounded support, then it will be exactly zero. So with such gradients, you cannot train anything. The generator will not improve. You will be simply stuck at that point. It will not improve. From this point, your training will simply stop, right? And it's a problem. It's an issue. It means that either you need to initialize very close to your actual data distribution, or you're stuck. Okay? Any suggestions how to improve this? Say it again, please. So the suggestion was to train the generator separately. So train it, then we need some loss function, right? So the discriminator gave us the loss function, and here we don't have a loss function. We can train it maybe with some, I don't know, with some arbitrary distance, but then, I mean, it might do something, but not necessarily. What I would propose here is, let's blur this distribution. Let's make them wider. Okay? So the problem is that we have non-overlapping supports. If we blur these distributions, they will have overlapping supports, and of course, then we'll have gradients to drive the update of the generator, right? So for example, if we have, how do we blur the distribution? So think of blur as convolution with something, some Gaussian kernel, for example. How do you get convolution in terms of, how do you convolve the probability density function with something? You're thinking too complicated. So let me explain what I mean. I have X distributed according to PD or PG, doesn't matter. Okay, let's take PD. And let's say PD is some crazy distribution like this. Now I would like to blur this thing with some distribution. Let me call it P epsilon. Let's say it looks like a Gaussian kernel. Okay, and as a result, I would get something like this. Okay, convolution. How do I? So what do I need to do to X in order to? So I would like to build another random variable that is distributed according to this distribution. No, don't remember. Okay, so let me do the following. I will take epsilon from P epsilon and statistically independent on X. So statistically independent on X. And I will simply sum X and epsilon. Okay? This is, sometimes it is called the convolution theorem and probability theory. Then this sum will be distributed according to what is written here, PD convolution with P epsilon. Okay? So this is how you do blur. You add noise, essentially. Okay? So let me denote it for short as PD epsilon here. You added noise with this desired distribution, and it blurred your distribution according to the shape of this PE, of the density of this noise. Okay? So you can imagine what will happen to my plot here if you do this, right? So let me just draw another plot. This is X. This will be my new data distribution. This will be my new generated distribution. So this is PG epsilon, which is PG convolution with P epsilon. And this is PD epsilon, which is PD convolution with P epsilon, right? You can see that here we have a plenty of overlap between the supports, high quality gradients that will allow us to update the generator. The problem is that if your original data distribution looked like this, of course this mod will be lost, right? So it's not really a solution, right? You lose high frequency details, so these minor details that you might care about, right? It might be some class of images that happens infrequently, but of course you want to be able to generate it. So somehow you would like to combine, you would like to enjoy both from the original distribution that has all the details in it and from the blur distribution that gives you good numerical performance, right? So what was proposed in this paper is essentially to take a few scales or a few widths of noise. Let's denote by S. Let's denote by S some collection of such noise distribution. Let's say PE comes from this set S. And then I will just modify what I wrote before. I will write a sum over S, expectation epsilon coming from PE, expectation of X coming from PD, log dx, but it's not dx now, it's dx plus epsilon, right? Plus the expectation, of course, it's everything under this sum here, plus the expectation over epsilon from p epsilon, e z coming from our noise distribution, log 1 minus d gz plus epsilon. Okay? And you can easily show that, again, the discriminator will have a closed form solution, but now instead of one density, it will be a sum of densities. Okay? And then if you, again, substitute this dx into the minimum, of course, you maximize this over d, and you minimize this over g. And if you substitute this solution, you will get the following. It will be the minimization of the Jensen-Shannon divergence of, now I need to normalize to keep it probability densities. It will be just this sum of PD and this sum of the blurred PGs. Okay? So the only modification I added is, of course, this sum, right? And imagine that S contains just one noise distribution, and that noise distribution is a delta. You fall back to the previous case, right? Okay? Okay, any questions? So essentially, we are now comparing between these distributions. Let me write it generically. P epsilon coming from this set X, from this set S, basically blur distribution, and here asterisk stands either for D or G. It's either the data distribution or the generated distribution. And of course, because of this blur, you have wider support and you have details, right? Because the original distribution, you can say that one of the PEs will be simply a delta distribution. Another PE would be, for example, a Gaussian noise with some covariance sigma and zero mean. Okay? So in that case, you enjoy both from this blurred widened distribution with big support, as well as from having the sharp details of the original distribution. Okay? So numerically, this should definitely be much more beneficial to solve this problem rather than solving the original GAN problem, right? So, of course, how you do it numerically, let me just illustrate it for two levels of noise. One, zero noise. Another one is some amount of noise. So this is my generator. I'm injecting random noise as the input. This is my X coming from PG. I'm adding here another branch, adding epsilon to it. Okay. And this is my X coming from PG epsilon. Okay. And here I will fit both to the discriminator, right? Because I'm discriminating both. So my now expression for the discriminator receives both distributions. This is my discriminator. And here again, I'm feeding the real data. So this is X coming from PD. And I'm adding noise to it, epsilon. And this is X coming from PD epsilon. And of course, the discriminator looks both at this data the fake data, and this data, the real data. Okay? So you're simply injecting noise in the standard GAN scheme. Now the question is, of course, are you going to get, so will this guarantee that you are getting the, at least if you are able to find the global minimum of this JSD, Jensen-Shannon divergence. So if it is 0, does it guarantee that what you generated is equal to the data distribution, right? So this is the big question. So because you're solving this minimization problem, how do you guarantee that you solve it and you get something completely different from what you are looking for? Okay, and I have a few minutes. I will show you a very simple proof of this fact. That's something that I adapted from the original paper. So again, we are measuring the distance between. Let's assume. So let me make some simplifying assumptions. I'm assuming that I have just one noise level. Okay, so my distance is measured between PD and PD convolved with PE. So I just have two of them. Of course, I need to write 1/2 here. And also 1/2 PG plus PG convolved with the same PE, P epsilon, sorry. And I'm assuming that P epsilon, that epsilon is distributed according to the Gaussian distribution with a positive definite covariance matrix and 0 mean. Okay, and of course it is IID, and epsilons are IID, and they are statistically independent of the data and the generated data. Okay, so statistically independent on Z as well. So in this case, yeah, I will also need to assume technically that PD and PG have supports bounded on some domain omega, or some basically that they have bounded support. So let me just write it by assuming that they are square integrable on omega, which is a meaningful assumption, I would say. Okay. So now let me denote PG as PD plus delta. Okay. Let me denote PG as PD plus delta, and essentially I would like to show that whenever this happens, delta must be 0. So if delta is 0, so delta is 0 if and only if PG equals PD, right? Delta is a function, of course, a function of x. Okay. Obviously, this function is also square integrable on omega, right? Quite simply. So I know that if this distance between, let me write it like this, it will be half PD plus PD convolution with P epsilon, and 1/2 PD plus delta plus PD convolution with P epsilon plus delta convolution with P epsilon. I know that this distance equals 0, okay? Which means that these two arguments are equal, right? So, of course, if they are equal, I can eliminate the same terms on both sides of the equality, and I get that P, let me write it like this, delta, let me write it as function of x, delta x plus delta convolution PE at point x equals 0, right? Okay. Or we can write it delta x equals minus delta x convolution with Pex. Okay. Now these are functions on functions defined on omega, right? X on omega. This is our support, our domain. I can take the Fourier transform on both sides and take the absolute value of this Fourier transform. So once I do it, let's denote the Fourier transform of delta as delta hat. The frequency parameter is omega, okay, equals to convolution becomes product, right, in the Fourier domain, and this is what we have, right? Now, and of course this identity has to hold for every omega. Now, what is particular about this delta? So we know that PG integrates to 1, right? And we know that PD also integrates to 1. Okay? So this means that delta integrates to 0. And signal processing people will say that delta has a DC response of 0. So if it integrates to 0, basically the integral over delta is its Fourier transform at omega equals 0, right? So essentially, I can say that for omega equals 0, of course, this equality holds trivially because it is 0 equals 0. Okay, so I only care about a non-zero omega. Okay, remember omega is a vector, right? So it's a non-zero vector. It has at least one component distinct from 0. So let's assume. So essentially, of course, the equality is trivial for omega equals 0. So let's assume that there exists some non-zero omega such that delta Fourier transform at this omega is not 0. Okay, I'm assuming something that will contradict my that contradicts something else, right? So and this will lead to the fact that delta hat omega is identically equal to 0 at every point. Okay, so let's assume that this is indeed the case. Remember that our PE is a Gaussian with this covariance matrix sigma. Its Fourier transform will also be a Gaussian with the inverse covariance matrix, but it doesn't matter whether it's inverse or not. It's the covariance matrix itself is positive definite, right? So let's take the absolute value of PE at point omega. It will be the absolute value of E to the power minus 1/2 omega transpose sigma inverse omega, right? And this is a quadratic form with a positive definite matrix with a non-zero argument. It has to be strictly greater than 0, strictly positive. Now, an exponential of something, negative exponential of something strictly positive will be smaller than 1, right? So this absolute value of the Fourier transform of the PDF, it is sometimes called the characteristic function of the distribution, is strictly smaller than 1. Let's now plug it back into our equality. Our equality is telling us that this delta omega equals delta omega times something that is strictly smaller than 1, right? Now this can only happen if these two absolute values are equal to 0, right? And we assume that delta at this point is non-zero. So of course this cannot be true. This is a contradiction. So from here we of course can deduce that delta at this point omega must be equal to 0, and we fix just some arbitrary omega, so this obviously will be true for every omega. Okay, so essentially we proved that PG equals PD. Okay, so the bottom line is that our this scheme basically minimizing this, adding noise, and then just training the regular GAN. So basically minimizing this Jensen-Shannon distance for the sum of the distributions, one blurred by noise and another one intact by noise. So just two levels give you first the numerical advantage of having wider distributions and therefore much more stable and useful gradients for updating the generator. And on the other hand, it preserves all the details of the original distribution, so that if you can bring this function to its global minimizer, it will actually give you the true data distribution. Okay, so this is a very useful trick for training GANs. It really works well. I don't know if it is so widely known, but it is really, it really stabilizes the whole thing. Okay. Any questions? Okay, good. So what I'm going to was it too complicated or too trivial?
Not trivial.
Not trivial. Okay. Well, maybe so maybe the proof. So if you haven't seen Fourier transforms, we are going to talk. We are going to talk about a very generic setting for Fourier transforms in a few weeks when we talk about learning on non-Euclidean domains. Okay, so I will define what Fourier transforms mean, and we'll do it for very generic domains such as graphs or manifolds. So basically, I will first show you the Euclidean case, and including the fact that convolution becomes product in the Fourier domain. Okay. So again, this proof is trivial if you know this tool. If you don't know this tool or don't remember how Fourier transforms work, just believe me that it is true. Okay. Anyway, so for the next week, let me say a few words about the next week, and then I'll finish. So for the next week, I will ask you to watch the reinforcement learning videos. Okay, so we are going to talk about a new regime, a new way of basically approach to doing the training. In this setting, we have some world, some system. Okay, so let me draw a world. Okay, and we have some agent. Let me draw an agent. Okay, so an agent that acts on this world. Okay, and so suppose we are playing a game, right? And in this game we might have some adversary that plays against us, or we are driving a car, and this is basically all the world that we are seeing from the windscreen of our car. So we are acting on this world by selecting some action. So let's say if we're playing Pac-Man, we can go left, right, up, down, and maybe we can shoot, right? So these are our actions. At every point in time, we can select one of these actions, and the world reacts by giving us some feedback that we can quantify in terms of what is called the reward signal. Let's say we are getting paid money, or somebody takes money from us if we did a bad move. And our goal is to select the optimal way of acting, the optimal behavior. This is called a policy. Okay, it can be deterministic, it can be stochastic. Basically, we need to determine the behavior of this agent. So the world is currently present in some state St. I'm assuming that I can fully observe this state, which is of course not true in practically every setting that you can imagine, but still it is still a very useful formalism to assume fully observable state. So I know in which state my game is found. For example, I can see all the pixels of my Pac-Man game on my screen. Okay, I will decide which action I'm going to act upon, and then I will receive some score increase, or they will eat me and I will die, and this will be of course a very negative reward. And essentially, I don't know the rules of this game, so I need to discover them. And I need to simultaneously discover the rules of this game and find the optimal behavior. Okay? So, of course, you find these problems in control theory. This is called optimal control. I have some system, and I would like to control it in some optimal sense with respect to some function of these reward signals. However, in control, I typically know this system. So I have some set of differential equations or some difference equations that describe my system. And this is called optimal control. Our setting is slightly more complicated. I also need to discover the system. So it's a combination of optimal control and what control people call system identification. And in the machine learning community, this goes under the term of reinforcement learning. Okay? So basically, we are going to formulate the mathematical machinery that is called MDP Markov decision processes that is required for formalizing this setting, then we'll see that because of this Markovian property that in the video I will remind you what exactly it means if you don't remember, we will see that we can do what is called dynamic programming to solve these problems, but unfortunately dynamic programming will be simply intractable because of the size of the state space. And then we are going to approximate dynamic programming by using neural networks. Okay, so that's all about reinforcement learning. Of course, there is a lot more about it, and we'll also see that we can have sort of a GAN type approach that is called actor-critic architecture. That we have some agent behaving according to a policy that he tries to optimize, and some critic that tells us how well we did. Okay, sort of a discriminator. Okay, and this is currently, at least variants of this approach currently give state-of-the-art performance in reinforcement learning. Okay, so you will see it in the videos, and then we'll discuss about some advanced topics. Okay, see you.